In information theory and coding theory with applications in computer science and telecommunication, error detection and correction or error control are techniques that enable reliable delivery of digital data over unreliable communication channels. Many communication channels are subject to channel noise, and thus errors may be introduced during transmission from the source to a receiver. Error detection techniques allow detecting such errors, while error correction enables reconstruction of the original data in many cases. Definitions. The general definitions of the terms are as follows. Error detection is the detection of errors caused by noise or other impairments during transmission from the transmitter to the receiver. Error correction is the detection of errors and reconstruction of the original, error-free data. History. An early systematic use of error detection was by Jewish scribes in the precise copying of the Jewish Bible, beginning before Christ. An emphasis on minute details of words and speakings evolved into the idea of a perfect text in 135 CE, and with it increasingly forceful strictures that a deviation in even a single letter would make a Torah scroll invalid. The scribes used methods such as summing the number of words per line and per page, and checking the middle paragraph, word and letter against the original. The page was thrown out if a single mistake was found, and 3 mistakes on a single page would result in the entire manuscript being destroyed. The effectiveness of their methods was verified by the accuracy of copying through the centuries, demonstrated by discovery of the Dead Sea Scrolls in 1947 to 1956. Dating from c. 408 BCE to 75 CE. Introduction. The general idea for achieving error detection and correction is to add some redundancy to a message, which receivers can use to check consistency of the delivered message, and to recover data determined to be corrupted. Error detection and correction schemes can be either systematic or non-systematic. In a systematic scheme, the transmitter sends the original data, and attaches a fixed number of check bits, which are derived from the data bits by some deterministic algorithm. If only error detection is required, a receiver can simply apply the same algorithm to the received data bits and compare its output with the received check bits. If the values do not match, an error has occurred at some point during the transmission. In a system that uses a non-systematic code, the original message is transformed into an encoded message that has at least as many bits as the original message. Good error control performance requires the scheme to be selected based on the characteristics of the communication channel. Common channel models include memory-less models where errors occur randomly and with a certain probability, and dynamic models where errors occur primarily in bursts. Consequently, error detecting and correcting codes can be generally distinguished between random error detecting, correcting, and burst error detecting, correcting. Some codes can also be suitable for a mixture of random errors and burst errors. If the channel capacity cannot be determined, or is highly variable, an error detection scheme may be combined with a system for retransmissions of erroneous data. This is known as automatic repeat requests, and is most notably used in the Internet. An alternate approach for error control is hybrid automatic repeat requests, which is a combination of ARQ and error correction coding. Error implementation. Error correction may generally be realized in 2 different ways. Automatic repeat request. This is an error control technique whereby an error detection scheme is combined with requests for retransmission of erroneous data. Every block of data received is checked using the error detection code used, and if the check fails, retransmission of the data is requested. This may be done repeatedly, until the data can be verified. Forward error correction. The sender encodes the data using an error correcting code prior to transmission. The additional information added by the code is used by the receiver to recover the original data. In general, the reconstructed data is what is deemed the most likely original data. ARQ and FEC may be combined, such that minor errors are corrected without retransmission, and major errors are corrected via a request for retransmission. This is called hybrid automatic repeat request. Error detection schemes. Error detection is most commonly realized using a suitable hash function. A hash function adds a fixed length tag to a message, which enables receivers to verify the delivered message by recomputing the tag and comparing it with the one provided. There exists a vast variety of different hash function designs. However, some are of particularly widespread use because of either their simplicity or their suitability for detecting certain kinds of errors. A random error correcting code based on minimum distance coding can provide a strict guarantee on the number of detectable errors, but it may not protect against a pre-image attack. A repetition code, described in the section below, is a special case of error correcting codes. Although rather inefficient, a repetition code is suitable in some applications of error correction and detection due to its simplicity. Repetition codes. A repetition code is a coding scheme that repeats the bits across a channel to achieve error-free communication. Given a stream of data to be transmitted, the data are divided into blocks of bits. Each block is transmitted some predetermined number of times. For example, to send the bit pattern 1011, the 4-bit block can be repeated 3 times, thus producing 1011, 1011, 1011. However, if this 12-bit pattern was received as 1010, 1011, 1011, where the first block is unlike the other two, it can be determined that an error has occurred. A repetition code is very inefficient, and can be susceptible to problems if the error occurs in exactly the same place for each group. The advantage of repetition codes is that they are extremely simple, and are in fact used in some transmissions of number stations. Parity bits. A parity bit is a bit that is added to a group of source bits to ensure that the number of set bits in the outcome is even or odd. It is a very simple scheme that can be used to detect single or any other odd number of errors in the output. An even number of flipped bits will make the parity bit appear correct even though the data is erroneous. Extensions and variations on the parity bit mechanism are horizontal redundancy checks, vertical redundancy checks, and double, dual, or diagonal parity checksums. A checksum of a message is a modular arithmetic sum of message code words of a fixed word length. The sum may be negated by means of a ones complement operation prior to transmission to detect errors resulting in all zero messages. Checksum schemes include parity bits, check digits, and longitudinal redundancy checks. Some checksum schemes, such as the DAM algorithm, the Loon algorithm, and the Verhoef algorithm, are specifically designed to detect errors commonly introduced by humans in writing down or remembering identification numbers. Cyclic redundancy checks. A cyclic redundancy check is a non-secure hash function designed to detect accidental changes to digital data in computer networks. As a result, it is not suitable for detecting maliciously introduced errors. It is characterized by specification of what is called a generator polynomial, which is used as the divisor in a polynomial long division over a finite field, taking the input data as the dividend, such that the remainder becomes the result. A cyclic code has favorable properties that make it well suited for detecting burst errors. CRCs are particularly easy to implement in hardware, and are therefore commonly used in digital networks and storage devices such as hard disk drives. Even parity is a special case of a cyclic redundancy check, where the single-bit CRC is generated by the divisor x+1. Cryptographic hash functions. The output of a cryptographic hash function, also known as a message digest, can provide strong assurances about data integrity, whether changes of the data are accidental or maliciously introduced. Any modification to the data will likely be detected through a mismatching hash value. Furthermore, given some hash value, it is infeasible to find some input data that will yield the same hash value. If an attacker can change not only the message but also the hash value, then a keyed hash or message authentication code can be used for additional security. Without knowing the key, it is infeasible for the attacker to calculate the correct keyed hash value for a modified message. Error-correcting codes. Any error-correcting code can be used for error detection. A code with minimum Hamming distance, d, can detect up to d-1 errors in a code word. Using minimum distance-based error-correcting codes for error detection can be suitable if a strict limit on the minimum number of errors to be detected is desired. Codes with minimum Hamming distance d equals 2 are degenerate cases of error-correcting codes, and can be used to detect single errors. The parity bit is an example of a single error-detecting code. Error correction. Automatic repeat request. Automatic repeat request is an error control method for data transmission that makes use of error detection codes, acknowledgement and/or negative acknowledgement messages, and timeouts to achieve reliable data transmission. An acknowledgement is a message sent by the receiver to indicate that it has correctly received a data frame. Usually, when the transmitter does not receive the acknowledgement before the timeout occurs, it retransmits the frame until it is either correctly received or the error persists beyond a predetermined number of retransmissions. Three types of ARQ protocols are stop and wait ARQ, go back NARQ, and selective repeat ARQ. ARQ is appropriate if the communication channel has varying or unknown capacity, such as is the case on the Internet. However, ARQ requires the availability of a back channel, results in possibly increased latency due to retransmissions, and requires the maintenance of buffers and timers for retransmissions, which in the case of network congestion can put a strain on the server and overall network capacity. For example, ARQ is used on shortwave radio data links in the form of ARQE, or combined with multiplexing as ARQM. Error correcting code. An error correcting code or forward error correction code is a process of adding redundant data, or parity data, to a message, such that it can be recovered by a receiver even when a number of errors were introduced, either during the process of transmission, or on storage. Since the receiver does not have to ask the sender for retransmission of the data, a back channel is not required in forward error correction, and it is therefore suitable for simplex communication such as broadcasting. Error correcting codes are frequently used in low-layer communication, as well as for reliable storage and media such as CDs, DVDs, hard disks, and RAM. Error-correcting codes are usually distinguished between convolutional codes and block codes. Convolutional codes are processed on a bit-by-bit basis. They are particularly suitable for implementation in hardware, and the Viterbi decoder allows optimal decoding. Block codes are processed on a block-by-block basis. Early examples of block codes are repetition codes, Hamming codes, and multidimensional parity check codes. They were followed by a number of efficient codes, Reed-Solomon codes being the most notable due to their current widespread use. Turbo codes and low-density parity check codes are relatively new constructions that can provide almost optimal efficiency. Shannon's theorem is an important theorem in forward error correction, and describes the maximum information rate at which reliable communication is possible over a channel that has a certain error probability or signal-to-noise ratio. This strict upper limit is expressed in terms of the channel capacity. More specifically, the theorem says that there exist codes such that with increasing encoding length the probability of error on a discrete memoryless channel can be made arbitrarily small, provided that the code rate is smaller than the channel capacity. The code rate is defined as the fraction k, n of k source symbols and n encoded symbols. The actual maximum code rate allowed depends on the error-correcting code used, and may be lower. This is because Shannon's proof was only of existential nature, and did not show how to construct codes which are both optimal and have efficient encoding and decoding algorithms. Hybrid schemes. Hybrid ARQ is a combination of ARQ and forward error correction. There are two basic approaches. Messages are always transmitted with FEC parity data. A receiver decodes a message using the parity information, and requests retransmission using ARQ only if the parity data was not sufficient for successful decoding. Messages are transmitted without parity data. If a receiver detects an error, it requests FEC information from the transmitter using ARQ, and uses it to reconstruct the original message. The latter approach is particularly attractive on an erasure channel when using a rateless erasure code.